So if you have this pipe and there's like some fluid going through this mixture of A and B, and somehow there's a high concentration of A, then there's like low concentration of A. So these two type of motion that's happening here would be the convection itself of the fluid flow, like the whole fluid is like going through, and then there's or diffusion of molecule A trying to go from high to low concentration. So if you're trying to represent that in terms of flux, we can make like some imaginary plane 1 here. So the flux, or to be specific, the molar flux of A would be the mole fraction. So the mole percentage of A that is in the mixture of A plus B times the total flux, which makes sense. So that's really showing the convection part. And then for diffusive flux part, we have the total concentration. Total concentration is referring to how much molecules are there in given the space. So for tire example, the more air we put it into the tire, the total concentration in that system is increasing. And then we have the DAB, the diffusivity of A in the infinitely dilute B, times the concentration gradient of A, the molar concentration gradient. And we have the negative because the gradient is always, it has a negative part in it, because if it's like the z-axis, like the actual coordinate, and then like the concentration, and let's say there's like high concentration, and then there's just like low concentration, and we can reasonably assume that it like try to go for like this direction. But so that's like the force that's trying to act on it. So in terms of coordinate is going from like from low to high, so that's like plus, but also there's like a concentration is going from high to low, so there's like the delta concentration is like negative. So it in total it has a negative term. Anyway, so that's why we have negative term here, is to cancel out the negative. So it's like actually adding the diffusive flux part into the convection flux part. But anyway, so that's how it is represented. And let's look at the velocity of the molecule A relative to like a stationary coordinate. So if you're doing the ship example, you are, or this whole system can be like a ship. So the ship, the fluid flow is happening, ship is like moving at some speed, and then you start like getting up and like start walking within the ship. So that would be the diffusion part. And this, what we're referring to, is like if you're observing myself or the molecule A from a lighthouse from afar, I'm moving at a speed of ship plus my walking speed, right? And then we have this U star, which is a molar average velocity, and that's kind of like equivalent to ship speed. And what it is that it's a mole fraction of A times velocity of this absolute velocity of A, and then the mole fraction of A, what? I think this should be B. So the mole fraction of B times the velocity of B, and we add them up, and then we have this molar, and then we take an average of it, and this molar average velocity. But I guess I said ship speed because like I'm such a small part of the ship, and the overall is just moving at a speed of ship. So, and then we have this U, which is a mass average velocities, and how we average is weight of particle A times the velocity, absolute speed of the particle A, plus the weight of the particle B times the velocity, absolute velocity of B, and we like add them up and average it out. And this matters because the ship is a lot heavier than I am, and this molar average, even though I may have like a same like one person moving, and then one ship. And in terms of molar, they're like same, and then the molar average velocity maybe a little higher, but in terms of like pure mass, like the energy kinetic energy perspective, the percentage of the ship speed is a lot greater, a heavier weight than myself. So that's why it's also useful to know the mass average velocity. The total flux of a particle A, we can define as the concentration of A times the absolute velocity of A, so like absolute speed. And we also have the diffusive flux, and that's where diffusion is basically like walking within the ship. So concentration of A times the my absolute velocity minus the speed of ship. So what we have is like the walking speed of myself, and that's basically the diffusive flux. In other words, how fast are you walking in the ship? So just to kind of like organize it into a table, so we have this mass transfer type of total versus like diffusion, and the basis could be based on the mass or mole, and flux. For mass system, we use a small, not capital, but we use a lowercase, and for mole based, we use a uppercase. And for total mass transfer, we use N. For diffusion, we use J. So for flux of total mass flux, we have Na equal density of A times the velocity of A, and the gradient will be based on the weight of A. And we get the total flux Na equal the weight of A times the N total minus the density times diffusivity of A, and then mass fraction gradient of A. And then mole, we have this going on where X is the it's a mole fraction, and this is the total concentration within the system of particles within the system, and diffusivity, and we have this gradient of the mole fraction, and so on. And why this? We call this system a frame of reference interpretation, and why it can be useful. One example is calculating how a system where there's an already there's like blood is flowing, and then we give a quick injection of some drug, and some distance later, if you look at this from here, and we look at the concentration of drugs within the system, if you're trying to do it like hydrodynamic calculation like Navier-Stokes and whatnot, it's like super complicated because there's like a blood flowing, and then there's also drug flowing, there's some diffusion, and then there's like it's just like complicated. But whereas if you use the frame of reference interpretation, and so if you follow the drug like it's like traveling down with like a camera, like, and then we just go side by side, and then like we look at it from here, we can see that this is like the X when X is 0, which is like the center of the drug, I guess. And at the center, the concentration of drug will be like the highest, and then it just goes low. It kind of follows the like natural bell curve. And it's just like a lot easier to do it that way. And we talked about like the molar versus like mass transfer type, and why we do that is this is one example. So we have this system where there's two containers that are connected with a pipe, and then valve is like closing in the middle. And on one end we have the 1 mole of helium, and the other end we have the 1 mole of SF6. And as you can see that this sulfur hexafluoride is a lot heavier than helium, so it's like the scale is tilted to the SF6. But when we open the valve, we can see that through diffusion, the scale will eventually be even, or it's like balanced, where there's like in total there's 1 mole of each molecule. So 0.5 mole of helium and 0.5 mole of SF6, and the same thing on the other side. And then each will weigh like about 7.5 grams, because 1 mole of helium weighs about like 4 grams. And then the 1 mole of SF6 weighs about 146 grams or so. I could be wrong, but approximately something like that. So if you're just looking at the molar flux, this has happened. So the molar flux of a helium would be the X, which is the mole fraction. I keep forgetting, so I'm going to write it down. X is a mole fraction times like the flux of helium plus flux of SF6, which makes sense because the total flux, and then we're just getting the mole fraction of helium to get it, and then minus the total concentration, as is again the same thing as tire, how much particles are within the system, which is constant, times the diffusivity of helium in the SF6, times the mole fraction gradient of helium, and that's like the diffusive portion. But we can simplify this equation because they are going to go to zero. Reason being is that for the equimolar counter diffusion principle states that the flux of helium would be same thing as the negative flux of SF6, which makes sense because there's like 1 mole and 1 mole at the end. It's going to be like 0.5 mole of each on each end, right? So in terms of molar scale, the 0.5 mole went this way for helium, and then 0.5 mole of SF6 went this way. So they're like basically the same amount, it's just a different direction. That's why there's a negative sign. So, and they're gonna, if you add them up, it's gonna go to zero. Because makes sense, because there's 1 mole and 1 mole at the beginning. At the end, there's 1 mole and 1 mole. So no flux, molar flux. And if this goes to zero, this mole fraction also goes to zero. And what we have left is a negative sign here, diffusivity of helium over here, and then the concentration gradient. And how this concentration gradient happens is the total concentration gradient times the mole fraction of the helium gives me the concentration gradient of helium. And this is basically, I think, the same thing as a diffusive flux of helium. But if we look at it from here, definitely some stuff has moved to here, and that's why it's a balance, right? So if you look at it from the mass scale, not in the mass perspective, instead of the mole perspective, so we have this total mass flux of helium, which is equal to the mass fraction of heliums times the mass flux of helium plus mass from SF6. So it's showing like the mass flux of helium, right? And then minus the density times the diffusivity of helium times the mass fraction gradient. So it's like now the concentration is not defined by the mole but by the mass. And through like some complicated math, we can get this diffusive mass flux of helium, where these are correctional factor, and we have this a similar diffusivity times the concentration gradient over here, where this is concentration of mass, and then we have the correctional factor, molecular weight, and mass fraction of helium, yada yada yada. And we can represent the diffusive mass flux, which of the system. And generally, rule of thumb is that for gas we use like molar basis of flux, and then for liquid and solid we use mass, which makes sense because gas is like tends to be, although we use gas for this example, but most gases in the system is like they have about the same density or not that different, whereas liquid and solid there's a wide variety of differences that could occur, and mass can be better suited for understanding the liquid and solid system